Okay guys, so welcome to the heating curve review for your test. This is a heating curve, and all heating curves have this shape. They go up, they plateau or flatten, they go up again, they plateau and flatten, and then they go up again. And this is because as you add heat energy to a substance, the temperature goes up in some places and stays still in others. And that's kind of surprising for most students. Most students think that if they keep heating something, it should keep getting hotter and hotter and hotter. But it doesn't, because there are two places where this substance is going to be using the heat energy we're giving it to change state instead of using the heat energy to get hotter or speed the particles up. So let's say we start out at negative 40 degrees down here, and this substance is in the solid state. So it's looking like this, these little particles up here, which are vibrating in place. And we start adding heat energy, and what those particles will do is they'll start to speed up. They'll move faster and faster, and we measure that as temperature. When they get to 0 degrees Celsius, the particles now have enough energy that they can rip apart their interparticle forces, and they can separate from each other a little bit, and they'll start to turn into a liquid. So in this state here, we've got both a solid and liquid particles, and during that entire time while the substance is melting, we're going to get a plateau. We're going to get a flat part of a graph, and that's because the particles are taking in heat energy. See, heat energy is increasing, but they're not using it to speed up anymore. Now they're using it to rip apart, like little magnets that have to pull apart from each other. They're going to change from one state to another. After everybody has turned into a liquid and everybody's now in the liquid state, and we have those little curved arrows, then the liquid can start heating up again because those particles can start speeding up again. So they're going to take the heat energy we're giving them now, and they're going to move faster and faster and faster until they get to that temperature here, 100 degrees. This is water, by the way. At 100 degrees, that water is now so hot, the particles are now moving so fast that they can just rip completely apart and start turning to a gas. So you can see some of the particles have turned to a gas. So we have liquid down here and gas up there. And this is boiling. During the boiling, when we move from liquid to gas, the particles are not speeding up. Instead, they're changing position. And then after they're done changing position, everybody's a gas. We can have temperature go up again because all the particles can pick up speed again. So there's different types of energy being used here. We're adding heat energy to the particles, but that heat energy is being used differently at different places. Anywhere you see the line going up, we're changing the kinetic energy of the particles. We're making them move faster. Any place where the particles are changing position, they're storing up energy for later, and that's potential energy. So think about that. A couple of questions you might get asked. One question might be, at what temperature does this substance melt? Well, for whatever substance it is, you're going to want to look to see where does the first plateau occur. Because if your substance starts as a solid, the first plateau temperature is the melting point of the substance. Now hold on to your hat, this is really weird. That's also the freezing point temperature. Water both melts and freezes at 0 degrees Celsius. And that's odd. A lot of students feel like that doesn't make any sense. How can something both melt and freeze at the same temperature? And that's because melting and freezing are just reverse processes of each other. They're melting and freezing if you took a snapshot of particles that were in the process of melting and another snapshot of the same particles that were in the process of freezing, they would both look like this. They'd be halfway between frozen and unfrozen. And that starts to happen at 0 degrees. So you can think of it this way. You could make a cooling curve that does the opposite, right? The cooling curve for this substance would start out over here as a gas at about 30, I don't know really what temperature this is trying, 130 degrees. My one got cut off. And it would cool off till we got to this temperature here, where it would start to condense and turn back into a liquid. When it all hits the liquid phase, it would slow down, cool down until it gets here and turns into a solid. After it was all a solid, it would cool down and the temperature would just drop continuously. That's the cooling curve. Notice how it has the exact same pattern in reverse, and notice that the plateaus are the same. On the cooling curve, we're boiling at this temperature, and we're condensing, which is the reverse of boiling, at that temperature also. Here on the cooling curve, when we go from liquid back to solid, we're going to freeze. Notice that freezing happens at the same temperature. Now, the only thing that's wrong on the cooling curve is these things, right? Instead of going from gas to liquid here, we'd be going from liquid to solid. This would be solid over here. Over here, we would still be in the liquid state. But over here, since we're now going this way, right? Over here, we're condensing. That means that during the condensing phase, we're going from gas to liquid. And over here, we'd be all gas. So you have to be able to identify at what temperature the different state changes are happening. So you need to know that melting and freezing both happen at the same temperature, and they're wherever your plateau happens to be. Condensing and boiling happen at the same temperature, wherever your plateau happens to be. Let's clear this picture up and do some practice. Okay, so what temperature does this substance condense at? At what temperature does this substance condense at? Well, condensing is the reverse of boiling. And this substance boils here. Whoa. Right here. And since it boils at that temperature, we know that that temperature is 100 degrees, right? That must mean that when it cools off, it'll also condense at that temperature. If it was a gas going back to a liquid, it would condense at 100 degrees Celsius. Here's another question. Pick two places on this graph where kinetic energy is increasing for the particles. Kinetic energy is the energy of motion, so when the particles are speeding up, kinetic energy is increasing. Where are the particles speeding up? Well, the particles are speeding up wherever you see a temperature increase, so anytime you see an up slope, kinetic energy is increasing. Where's potential energy changing or increasing? That's when the substances are changing position and the particles store up energy when they do that. Here's another question I might ask. Could you draw a picture of what the particles look like at a particular point? To do that, let me move my graph up so you can't see the pictures. Okay, here we go. So, what do the particles look like at, let's say, at 60 degrees or so, which would be around here. Right around here, 60 degrees. What would you draw if you had to draw what the particles look like at 60 degrees? Well, you'd come over and see, what state am I in? Oh, I'm a liquid, all liquid. So let's take 6 particles of a liquid. They're fairly close together, and they have to have curved arrows to represent the liquid particles. What if I wanted you to tell me what the particles look like at 120 degrees? What do those particles look like at 120 degrees? Well, now at 120 degrees, we're a gas. Gas particles are more spread out from each other like this. I should probably do 6 since I did 6 before. And they have that straight line motion. Okay, one last question I might ask. Could you draw the reverse of this? Could you draw the cooling curve? Go ahead and just mentally sketch what you think it would look like if you were to draw right on top of this what the cooling curve looked like. Here we go. It's a gas cooling off. Then it's got to be changing state here, cooling off, changing state here, cooling off. Those plateaus have to happen at the same temperatures. So you can almost kind of just draw your plateaus in and then connect your lines. And it should look like just the exact opposite of the pattern that you had before. And you should be able to label it too. You should be able to say, okay, this is a gas. this is going from what state to what state, from here to here. Well, if this was a gas over here, it's going to be going from the gas back to the liquid. Here it's going to be all liquid as we cool off. Here it's going to be a liquid turning back to a solid. And here it's going to be all solid. Okay, hopefully that has helped you understand heating curves and cooling curves a little bit better for your test. See you in the next tutorial.